All right, I want you to look at the crystals on the left-hand side. They look like regular, normal crystals. But if you look really close, that is a man. That is a full-size grown man that is in these giant crystals. This chapter, what we're going to do is we're going to determine the number of valence electrons in an atom of a representative element. We're going to explain the octet rule, which is the only new thing. That and dot structures. We're going to describe how cations form, and we're going to describe how anions form in this section of the chapter, ions.
About 15 years ago, when a mining company started pumping water out of a cave 300 meters below Nica, Mexico, they were hoping to find lead or zinc or maybe some silver. Once they finished pumping the water out, though, they realized that they weren't going to be mining anything from this cave, mostly because of the giant 12-meter-long spikes everywhere. The spikes were actually huge crystals, the largest ever found. And the pillars of mineral, as big as 3-story buildings, weren't the only hazard in the cave. If you managed to make the same descent the miners did, you'd only get to see the crystals for about 10 minutes, because that's roughly how long a human can survive unprotected in the cave. The appropriately named Giant Crystal Cave was discovered in 2000 when miners were drilling a tunnel to expand their mine. They'd already pumped the water out of the area, and as they blasted through the rock, they revealed the 30 by 10 meter cave containing enormous crystals of selenite, a crystal form of the mineral gypsum. The conditions in the caves are a collection of extremes. The thermometer reads about 58 degrees Celsius on a good day, and the humidity hovers around 100%. The cave contains hundreds of crystals, some up to 12 meters long and weighing about 50 metric tons. It's so hot and humid in the Giant Crystal Cave that the insides of your lungs would actually be the coolest surface around. So the water vapor in the air would condense in your lungs as you breathed, and that is not a great thing to have happen to you. Essentially, if you stayed in the cave long enough, you'd drown in your own lungs. So understandably, these conditions make scientific research kind of tough. Scientists have to go in there with custom-made, super powerful refrigeration suits, but even those only buy them about a half an hour at a time. So we still have a lot to learn about the cave and what's in it, maybe even forms of life we've never seen before. It might seem unlucky that the cave with the largest crystals in the world is so inhospitable, but those conditions are actually the perfect nursery for these mineral formations. The cave lies deep beneath Nica Mountain, which formed about 26 million years ago from volcanic activity, and all that molten lava came with a bonus: a whole lot of anhydrite. Anhydrite is the dehydrated form of the mineral gypsum. Both compounds have the same chemical makeup, except for the anhydrite is missing water. But if conditions are right, anhydrite can absorb water and become gypsum. And if the anhydrite turns into gypsum slowly enough, it will crystallize to form selenite, just one of the many forms that gypsum can take. The real key to this process is temperature. If it's above 58 degrees, anhydrite will be stable and just sit there, but at or below 58 degrees, it'll begin to dissolve and use the water in the environment to essentially reform into gypsum. And that is exactly what happened in Giant Crystal Cave. Once the magma beneath the mountain cooled to around 58 degrees, the anhydrite began dissolving very, very slowly. Then new particles of hydrated gypsum began to form as crystals of selenite. Now, other caves in this same mountain, like the one with the particularly boss name of Cave of Swords, also contained lots of selenite crystals. But the crystals there are only about a meter long because that cave cooled more rapidly, so the hydrated gypsum formed too quickly to deposit as very large crystals. But Giant Crystal Cave was just deep enough in the ground to stay at the transition temperature. Since the cave was around 58 degrees for about 500,000 years and filled with anhydrite-rich water, the selenite crystals just kept on growing until the year 2000, when we pumped the water out. Technically, there's no limit to how big the crystals can get in such perfect conditions, so when the mine eventually closes and we stop pumping the water out of the cave, the crystals will again start growing. Thanks for watching this SciShow dose. If you have an idea for a weird place that you'd like us to explore and share with the world, let us know in the comments below or on Facebook or Twitter or Tumblr. And don't forget to go to youtube.com/scishow and subscribe.
All right, valence electrons are the electrons in the outermost occupied energy level and are involved in ion formation. Now remember, the outermost are only the s and p electrons in an electron configuration. For a representative element, the group number equals the number of valence electrons. Now, that is groups 1A through 8A. That is the S and the P sublevel elements. An electron dot structure shows the symbol of the element and its valence electrons. Atoms will tend to gain or lose the number of electrons that will provide the atom with a noble gas electron configuration. For example, phosphorus is neon 3s2 3p3, and the phosphide ion, where it gains 3, it goes from 3p3 up to 3p6, which is the same as that of argon.
Valency. Objectives: to study valency and valence orbit. Tendency of an atom to complete its octet configuration. Calculations of valency of an atom and an ion. According to Niels Bohr, electrons in an atom are arranged in a region around the nucleus called energy levels, orbits, or shells. These orbits are represented by letters such as K, L, M, or by numbers 1, 2, 3, and so on. The number of electrons present in the outermost orbit are known as valence electrons, and the outermost orbit is called the valence orbit. The maximum number of electrons that can be accommodated in the outermost orbit is 8. The elements with completely filled outermost orbits containing 8 electrons are said to possess an octet configuration. Such elements do not combine with other elements easily, and hence show very little reactivity. Therefore, they are said to have a zero combining capacity. On the other hand, the elements with incompletely filled valence orbits have a tendency to complete their octet configuration by combining with atoms of the same or different kind. This capacity of an atom to combine with another atom is called its valency. Elements combine with other elements by losing, gaining, or sharing their electrons. For example, electron configuration of sodium is 2, 8, 1. And that of chlorine is 2, 8, 7. Sodium finds it easier to lose 1 electron rather than gaining 7 electrons to complete its octet, while chlorine easily accepts an electron rather than losing 7 electrons to complete its octet. Thus, both sodium and chlorine have a valency of 1, as their combining capacity is 1. On the other hand, consider 2 chlorine atoms having electronic configuration 2, 8, 7, approaching each other. As you can see, each chlorine atom needs 1 electron to complete its octet. In this case, instead of gaining or losing electrons, both the chlorine atoms share 1 electron each. Hence, the valency of both the chlorine atoms in a chlorine molecule is 1, as their combining capacity is 1. Thus, the number of electrons gained, lost, or shared to complete the octet directly tells us about the combining capacity of the element, that is, its valency. Let us now calculate the valency of an atom. We will first study elements having more than 4 valence electrons. Consider an atom of fluorine with atomic number 9 and an electronic configuration of 2, 7. Fluorine thus has 7 valence electrons. In order to calculate its valency, the number of valence electrons are subtracted from 8. Hence, the valency of fluorine is 1. For an oxygen atom with an atomic number 8 and electronic configuration of 2, 6. Its valency is given by 8 minus 6, that is 2. Now we will study those atoms which have less than 4 valence electrons. Consider an atom of sodium with an atomic number 11. It has an electron configuration of 2, 8, 1. Thus, sodium has one valence electron. For such atoms, their valencies are equal to the valence electrons. Sodium thus shows a valency of 1. It should be noted that valency of both sodium and fluorine is 1. But sodium loses an electron while fluorine gains an electron in order to complete their octets. Hence, valency of sodium is considered to be positive, whereas that of fluorine is negative. Let us now see how the valency of ions is calculated. In the case of ions, their valencies are the same as the charges carried by them and are expressed with proper signs. Species carrying positive or negative charges are called ions. Those which carry positive charges are known as cations. Some of the simple cations are Na+, Cu2+, Al3+, etc., and hence they have valencies of +1, +2, +3, respectively. The species carrying negative charges are called anions. The examples of anions are Cl-, O2-, etc., showing valencies of -1 and -2, respectively. Moreover, there exists a group of atoms carrying a charge known as a polyatomic ion. For example, NH4+, SO42-, PO43-, etc. They show valencies of +1, -2, and -3, respectively. Summary. We have studied that the number of electrons present in the outermost orbit are known as valence electrons, and the outermost orbit is called a valence orbit. The maximum number of electrons that can be accommodated in the outermost orbit are 8. Elements with incompletely filled valence orbits have the tendency to complete their octet configuration by losing, gaining, or sharing their electrons. This capacity of an atom to combine with another atom is called its valency.
What are valence electrons? Now, we've talked about these before. Valence electrons are the outermost electrons in an atom, and it is only the s and p electrons. D and f electrons are never valence electrons. The valence electrons largely determine the properties of an element and are usually the only electrons used in bonding. Is the following sentence true or false? The group number of a representative element in the periodic table is related to the number of valence electrons it has. That is true, because if it's in group 1, it has 1 valence electron. If it's in group 2, it has 2 valence electrons, etc. What is an electron dot structure? This is something new. The electron dot structure is a diagram that shows the valence electrons of an element as dots. So, if we wanted to do a valence electron diagram or an electron dot structure, the way it's going to look is you look at the group number, which tells you the number of valence electrons, and however many valence electrons it has, that's how many dots it has, up to a maximum of 8. So I'm going to give you some examples. Now, if you look at this, this is the S sublevel, which is groups 1 and 2, and the P sublevel, which is groups 13 through 18, which are also called 3A through 8A. And if you look at each column, each symbol has 1 dot in the first column, because that's group 1, they have 1 valence electron, because they're all S1 elements. And then group 2 has 2 dots because they're S2 elements. Group 13, also 3A, has 3 dots because they're S2 P1, which is 3 of them. Then group 14, 4A, has 4 dots because it's S2 P2. And then group 15 has 5 dots, 16 has 6, 17 has 7, and all of them except helium have 8 in group 18. But you'll notice that there's no pairing of valence electrons until you reach group 15 or 5A. So they did this to try to simulate what's going on with Hund's rule, where the electrons want to be as far apart as possible. So when you're drawing dot structures, the same thing would come into effect. So we're going to try. Now, we're going to practice some. But remember, group 1, 1, group 2, 2, group 13 through 18 are 3 through 8. So we want to do argon. So I look on my periodic table. I find argon. It is in group 8, so it's going to get 8 dots. So I put 2 on the top, 2 on the bottom, 2 on the left, 2 on the right. Calcium, I look for it. It's number 20. It's in group 2, so it gets 2 dots. But remember, they don't get to pair until they hit 5, because you have 4 different areas to put them. So like Hund's rule, they want to stay as far apart as possible. That's going to happen. So iodine is in group 7, so I'm going to put 3 pairs and a single. Now I have it drawn with 3 pairs and a single on the left. It doesn't really matter where the single one goes, as long as you have 3 pairs and a single, you're okay. Now, all atoms want to obey what's called the octet rule. The oct in octet means 8. So what's going to happen is when you form a compound, atoms are going to achieve the electron configuration like argon, which has 8. And that's the octet rule. They want to achieve the electron configuration of a noble gas. So they're either going to gain, lose, or share to do such. Metallic atoms tend to lose their valence electrons. So calcium is a metallic atom. So if it was going to form an ion, it would lose those 2 dots, because metals lose because they form cations. Most nonmetallic atoms achieve by gaining or sharing. So if I wanted to do iodine, I would either have to gain an electron from a metal or share with another nonmetal.
I want to talk to you guys about a basic rule in chemistry called the octet rule. So we know that atoms love to be stable, and the way an atom can achieve stability is by having a complete number of electrons, valence electrons, in the outer energy level. These valence electrons will allow atoms to have different properties. The octet rule states that an atom will gain or lose electrons to obtain 8 electrons in its outer shell. In other words, elements want to reach an electron configuration of the nearest noble gas. The word octet means a group of 8. For example, an octopus is an animal with 8 legs. An octagon is a shape with 8 sides. So let's look at a model of an atom. We know that an atom has a nucleus, where the protons and neutrons are located. Around the nucleus, we know that there are electron shells where all the electrons are located. The first electron shell in an atom can hold 2 electrons maximum. The electrons in the outermost shell are called valence electrons, which determine the properties of the atom. The second electron shell can hold a maximum of 8 electrons. In this case, the electrons in the second electron shell are called the valence electrons. The third electron shell can also hold a maximum of 8 electrons. In this case, the electrons in the third electron shell are called valence electrons, and so on. So let's look at the element lithium. Lithium is in group 1 of the periodic table, and since it's in group 1, it has 1 electron in its outermost shell. Another example is an element that is in group 16 of the periodic table. It will have 6 valence electrons. Elements in the same column as group 16 will also have 6 valence electrons. This is a general way to figure out the number of electrons for an element. Elements like to be in their most stable electron configuration. So the easiest thing for lithium to do is lose that 1 electron in its outermost shell to obtain the electron configuration of the noble gas helium. Helium is a very stable element because of its electron configuration. Sodium, like lithium, is also in group 1 and has 1 valence electron. Notice the lonely valence electron in the third shell of the atom. This shell needs 7 more electrons to satisfy the octet rule, but the easiest thing for sodium to do is lose that electron if it can. And when it does, sodium will now have the electron configuration of the noble gas neon. Now let's look at chlorine. Chlorine is in group 17, which indicates it has 7 valence electrons. So looking at the chlorine atom, notice how the outermost shell needs 1 more electron to satisfy the octet rule and have 8 electrons to be stable. That's why chlorine is a very reactive element, because it just needs 1 more electron. And when it does, it will have the stable electron configuration of the noble gas argon. And that is the octet rule.
All right. To form cations, we're going to do some metals first. So we want to write the electron configuration of the metals and circle the electrons that are lost when they form the cation. So I look up magnesium. It's number 12. I see its electron configuration is a neon core 3s2. Now, when it's going to lose its electrons, it wants to be just like the nearest noble gas, neon. So it's going to lose 2 to go from 12 electrons to 10 electrons. The 2 electrons that it loses are those 2 out there. When it does so, it becomes magnesium plus 2 because it now has 2 more protons than the electrons. It has 12 protons, 10 electrons. 12 minus 10 is plus 2. Aluminum. It's right next door. It's its next door neighbor. It's got 13, so it's 3s2, 3p1. Well, aluminum, its nearest noble gas, is also going to be neon, so it's going to lose 3 electrons, the 3s2 and the 3p1. And when it does that, it now becomes aluminum plus 3 because aluminum has 13 protons and the ion only has 10 electrons. 13 minus 10 is plus 3. Then I do potassium. It's in argon 4s1. So that's number 19, 4s1. I'm going to lose that 1 4s electron, which makes me K plus or K plus 1. We usually don't write the numbers because when number 1, because it's sort of like when you write H2O, you don't write subscripts of 1, we don't write superscripts of 1. We just say if it's a plus, it means plus 1. So now, I want to do the electron configurations of some of the noble gases. You'll notice that all of these, except the top one, have S2P6, which means they have 8 valence electrons, which means they're noble gas configurations. So argon, I look it up, it's number 18. So I go here and I want to find where it is. I also see that it's at the end of the 3rd row. So I can do several things. I can go here and I can count. I can count C is 2 plus 2 plus 6 plus 2 plus 6 is 18. Or I can go by the fact that it's the last numbers written are 3s2 and 3p6 and it's the end of the 3rd row. That's the easiest. So helium's the end of the 1st row. So the one that fits that is A. Neon is the end of the 2nd row. So that's going to be my 2s2, 2p6. And krypton is the end of the 4th row. So that's my 4s2, 4p6. What is the electron configuration called that has 8 electrons in the outermost level of all of its orbitals filled? And we keep saying this, the configuration that has 8 electrons in the outermost filled is the noble gas configuration. Now, I want to do the electron configuration for zinc. When I write the electron configuration for zinc, I see that it's argon 3d10 4s2. Now, the ion that zinc would form would be a plus 2 ion because it would lose those 2 4s electrons, which would then leave argon 3d10 because it's going to lose the s. It doesn't lose the inner electrons for zinc. Now, we have an energy level diagram written for copper. And you see it's there. And if you wanted to, you could go 1s2, 2s2, all that stuff, or you can just look. I want to find the electron configuration for the copper 1 ion. Well, the copper 1 ion is going to lose that 4s electron. So its electron configuration would be everything except that 4s electron. Now remember, the 4s in energy is lower than the 3d, but it's still the outer shell is the 4s. So that's the one that you would lose to go from copper to copper 1. Atoms of most nonmetallic elements achieve noble gas configurations by gaining electrons to become anions, or negatively charged ions. What property of nonmetallic elements makes them more likely to gain than lose electrons? The fact that most nonmetals have more than 4 valence electrons, and it's easier to gain to go up to 8 than to lose to go to 0. Is the following sentence true or false? Elements of a halogen family lose 1 electron to become halides. Now you have to remember back to chapter 6. The halogen family is group 7A or 17, and they are nonmetals. So that would be false because nonmetals would gain 1 electron to become halides, which are negative. It would lose it if it were a metal, but it's a nonmetal. So now, we want to know how many electrons each element will gain to form an ion. So nitrogen, I find nitrogen is number 7. It's also a group 5 or 15 element. So I'm going to go, it's a nonmetal. It's in group 5, which is more than 4 electrons. So how do I get to 8? I gain 3. Oxygen, its next door neighbor. It's in group 6. Group 6 is going to gain 2. Sulfur is below oxygen. It's also a group 6, so it's also going to gain 2 electrons. And bromine, which is a group 7, is going to gain 1 electron. Now, underneath 20 are the names of the ions that these metal or nonmetals form. Nitrogen becomes the nitride ion, oxygen becomes the oxide ion, sulfur becomes sulfide, bromine becomes bromide. That IDE is telling you that it's an anion. So when I do this, I want to write the symbol and the electron configuration for each ion and the noble gas that matches it. So nitrogen is number 7. So it's going to gain 3 to go up to 10. So I'm going to have N minus 3 as my charge because I'm gaining 3. I'm going to now have the electron configuration of 1s2, 2s2, 2p6, because remember, anions will always end in p6. So the 1s2, 2s2, 2p6, 2 plus 2 plus 6 is 10, and 10 equals neon. Oxygen, its next door neighbor, I'm going to throw them up here and show you. It's going to be a minus 2 because it's gaining 2. If you look at the electron configuration, because it's in the same row, it's going to end up having the same electron configuration of 1s2, 2s2, 2p6, which is 10, which is neon also. So now I want to do sulfide. Sulfide, it's 2 electrons gained, so it's s2 minus. Now it is in the 3rd row, so it's going to get a 3s2, 3p6 as its ending, because it's going to go from 16 to 18, and 18 just happens to be argon. Bromide, it's gaining 1, so it's Br minus. I look at the electron configuration for bromine, it's 3d10, 4s2, 4p5, so I go up to 4p6, which is... All right, we've got the formation of ions worksheet. We have a Ca atom and a Ca ion. We have an O atom and an O ion, and we've got all kinds of information about the number of electrons, protons, electron configurations, and such. The names of the 2 elements, Ca, I look it up, it's calcium. O is oxygen. Are the elements shown on the left sides of the 2 equations neutral? The answer is yes. And the way you can tell is if you look at the electrons and protons, they're equal. When the protons equals the electrons, they balance. So the positive balances the negative, so it's equal to 0. So number 3, what is the name of the energy to remove these electrons? Each of them have the energy called ionization energy. It's the energy needed to form an ion. What kind of charge does calcium take? Calcium is going to be a +2, and it's a cation. Because remember, when you lose electrons, you become positive, and positive ions are cations. What kind of charge does O take? Well, I look at the O ion, and next to it is 2 minus, and we call that an anion. What is the outer electron configuration of the calcium atom before? Very stable. How can you tell? And I'm going to say no, it's not, because when I look at the calcium atom, I see 4s2 all by itself. In order to be configurations that are stable, they would be s2p6s, not s2s, not p4s, as you're seeing up there. Is the outer electron configuration of the O atom before very stable? No, because once again, it is not a noble gas configuration. If it was an s2p6, we'd be perfect and we wouldn't have to do much, but that's not how it works. Number 8 is the electron configuration of the calcium ion after very stable. Yes. And how you can tell is when you take away those 4s2 electrons, you're left with 1s2, 2s2, 2p6, 3s2, 3p6. Whenever you have a 3s2, 3p6 or a 4s2, 4p6, if you have 2 s's and 6 p's, you're stable, you're like the noble gas. And since calcium's nearest noble gas is argon, you can see its configuration becomes the same as that. Now, for oxygen, it is going to be the same as neon, because what I'm doing is oxygen's going to gain 2. So my 2p4 is going to go up to 2p6. And then I have my s2p6, which is my octet rule. So that is stable. What is the electron configuration for the calcium ion? We already did that in number 8. What neutral atom has the same configuration? We did that in number 8. And in what chemical family is it located? That would be the noble gas. What's the electron configuration for O? Everything that we did in number 9. Answers number 11. Now, we formed ions. Now we're going to turn them into compounds. We're going to go into ionic bonds and ionic compounds. We're going to explain the electrical charge of an ionic compound and then some properties of ionic compounds. An ionic compound is made up of anions and cations that has an overall charge of 0. That is the main thing for ionic compounds, is whatever cation you have and anion you have, the overall positive negatives must balance to 0. The attraction between an anion and cation is called an electrostatic attraction. The representative unit for an ionic compound is called a formula unit. It's the formula and it's a unit of an ionic compound. They're not very creative when they come up with these names. A formula unit of an ionic compound shows the ions in their lowest whole number ratios. That's why you can write formulas for chemical compounds, because they're in whole number ratios. It's not H1.5O, it's H2O. Same thing, it's not Na.5Cl, it's NaCl. It's whole number ratios. Now, the properties of ionic compounds. Ionic compounds have characteristic properties that distinguish them from other substances. The first one is most ionic compounds are crystalline solids at room temperature, like salt, like sodium chloride. In general, ionic compounds have very high melting points because they have very strong attraction for one another. So if you were trying to melt, let's say, sugar, it's not an ionic compound. You can melt sugar over the stove. But if you tried to melt salt, it would not melt over a common household stove because the melting point is too high. Ionic compounds conduct an electric current when they are molten. Like I said, when they are turned into a liquid, that's what molten means, or in an aqueous solution. Aqueous solution is where it's dissolved in water. And the reason why is because those ions are free to move. So when you put salt in water, it dissolves into that water and it becomes sodium ions and chloride ions. And that's why it will conduct an electric current. But if you were to put sugar into water and dissolve it, it would not be free as ions because sugar is not an ionic compound, it's molecular. Now, I'm going to let Dan show you some conductivity of some solutions, and then we're going to talk about which ones are conductive versus non-conductive.
Oh, hi! Today we're going to learn about solutions and how they conduct electricity, or don't. Tap water. Distilled water. Huh? What? Salt water. 1 teaspoon per cup. Ooh. Hydrochloric acid. Nice. Sodium hydroxide. Ooh, just as concentrated. Sugar water. Sweet. Vinegar, a weak acid. Ethanol, a dissociative that doesn't dissociate. Don't try this at home. Barium sulfate. It's insoluble. No conductivity here.
So, he had several solutions: tap water, sodium chloride solution, hydrochloric acid, sodium hydroxide, and vinegar were all conductive. That's because they will either form partial charges or full charges, where distilled water, sugar, ethanol, and barium sulfate were non-conductive because they don't form ions in water. Barium sulfate doesn't dissolve in water, so because it doesn't dissolve, it doesn't break into the ions that make up the compound. The other compounds are considered molecular compounds.
When a piece of sodium metal is added to a flask of chlorine gas, the vigorous reaction that takes place releases a lot of energy, and sodium chloride, common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. As soon as the metal and nonmetal make contact, the process begins. When the chlorine molecules land on the sodium surface, they separate into individual chlorine atoms, each lying next to a sodium atom. Focus on one pair of atoms to see the key event in the formation of an ionic compound: electron transfer from the metal atom to the non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the particles that result attract each other and release energy. The loss of the electron converts the sodium atom into a smaller positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger negatively charged chloride ion, Cl-. Let's view this essential step once more. This electron transfer process occurs between all the other sodium and chlorine atoms as well. The large quantities of energy released vaporize tiny clusters of ions, and these attract others to release more energy. These clusters, which eventually aggregate and coat the walls of the flask, consist of the regular array of ions that make up crystalline sodium chloride.
All right. Sodium chloride is the most common known ionic compound. And when you're making an ionic compound, you have to know what an ionic bond is. So an ionic bond is the electrostatic forces that hold ionic compounds together. So the transfer of electron from the sodium to the chlorine, which forms the sodium ion and the chloride ion, that is called an electrostatic force. In an ionic compound, the charges of the cation and of the anion must balance to produce an electrically neutral substance. Please write that down or put a star next to that, because that is the whole basis of forming ionic compounds, is the total positive equals the total negative, which then gives you a zero overall charge, which is a neutral substance. Now, we want to do the dot structures for beryllium fluoride formation. So I've done the first ones for you. On your notes, I want you to put 2 dots by beryllium and 7 around each of the fluorines, because beryllium is in group 2 and fluorine's in group 17. Now, what you see to the left of that is the example of beryllium fluoride as it forms in nature. So what's going to happen is the beryllium is the metal. It's going to give up those 2 electrons. So watch. The first electron is going to go to the first F, and the second electron is going to go to the second F. Now, beryllium has no more outer electrons. Fluorine now has 8 outer electrons. So to show that this electron transfer has occurred, is what we're going to do is we're going to put brackets around each of the species. Now this is on the right side. On the right side, I want you to put brackets, and then around each of the F's, put 8 dots and a bracket. And then to show that the transfer occurred, the BE becomes +2 because it lost 2. And each F becomes -1 because they each gained 1. So if you do a little math, +2 -1 -1, you get 0. So the way that we show this in chemistry is like this. Beryllium with a +2 charge plus 2 F minuses equals BeF2. Now, the way that you do the math is there's one Be, so I put +2. And then notice I have 2 times -1, which would give me -2. 2 minus 2 equals 0. That's the whole goal of formation of ionic compounds. Now, you could do these over and over and a whole bunch of them, but they all work the same. A chemical formula shows the types and number or numbers of atoms in their smallest representative unit. Now, number 6 has 4 different compounds. And what we're going to do is I'm going to name the compounds, but we're going to just tell me the numbers and types of atoms represented by each of the formulas. Now, the first one is iron 3 oxide, aka rust. And it has 2 irons and 3 oxygens. Now, people are wondering when they do this, why are we just going through and putting down the numbers? When we get to balancing equations, these numbers of atoms are going to become very important. So we're going to practice it now. Now, as I said, that is iron 3 oxide. KMnO4. When I look at that, I have 3 different elements. I have K, Mn, and O. So I have 1 K, 1 Mn, and 4 O's. The subscripts are telling you how many of the atoms to the left of that exist. And that is called potassium permanganate. The third one has 1 carbon and 3 hydrogens. That's not even an ionic compound because carbon and hydrogen are both nonmetals. The next one, NH4NO3, and then people look to go, where'd I get 2 N's? There's 1 at the beginning, 1 in the middle. Then I have 4 H's and 3 O's. That is called ammonium nitrate. A formula unit is KMnO4, Fe2O3, NH4NO3. Those are all formula units. They're the lowest whole number ratio of ions in an ionic compound. But for CH3 is not even an ionic compound, so it's not really a formula unit. That would just be a molecular formula. Explain why the ratio of magnesium ions to chloride ion in MgCl2 is 1:2. Well, magnesium becomes +2. Chlorine is -1, so therefore you need 2 Cl- to balance the 1 Mg+. Okay, describe the structure of ionic compounds. Now, I told you before, one of the properties of ionic compounds is that they are solid crystalline structures. So an ionic compound is a collection of cations and anions arranged in a repeating 3D pattern, which we call crystals. Most ionic compounds are crystalline solids at room temperature, like sodium chloride, potassium chloride, sodium hydroxide. They're all crystalline structures. True or false? Ionic compounds have low melting points? No, we said that's false. We said they have very high melting points because of their strong interactives between the 2 ions. Circle the letter of each statement that is true about ionic compounds. A, when dissolved in water, conducts electricity. That's true as long as it dissolves. B, when melted, it does not conduct electricity. That's false, because when they are molten or melted, they do conduct electricity because the ions are now free to move. C, ionic compounds have very unstable structures. No, that's false. That's why they have very high melting points, because they're very stable. And D, ionic compounds are electrically neutral. That's true, because when your positives equal your negatives, you have a complete balanced formula. Now, we're going to do something like what we did before, but this one's a little bit done for you. We have magnesium and 2 chlorines. Now you'll notice the magnesium on the left has 2 dots, each chlorine has 7, so 1 electron is going to go to each of the Cl's. So on the right it gives me Mg plus 2 Cl minus. There should be another minus at the end. Please draw that in there. How many valence electrons does a neutral magnesium have? 2. You see the 2 dots. You can see it on all 3 of the examples. What is the charge on the magnesium ion? As you see at the top, it's plus 2 because it's in group 2. What does magnesium do in order to form an ion, and why does it tend to do so? It's going to lose its 2 valence electrons, so it gets that noble gas configuration. Those brackets up there that you see that we draw are showing that it's like a noble gas. Because remember, when we do electron configurations, we do the noble gases in the brackets, so this is indicating the same thing. Number 3, how many valence electrons does a single chlorine atom? Well, when I count before you look at the arrows, there's 7. Number 4, what's the charge of a chlorine ion? Well, when you look at the top, except for the fact that there's 1 missing, it's going to be a -1. What does it do, and why does it do this? It gains 1 to make 8 outer electrons. You'll notice that my anions have 8 dots, where my cations have 0 dots. It's very important when you're doing dot structures. If you go back to look at BeF2, you'll see the same thing. The Be on the right has no dots but a +2 charge, and the Fs each have 8 dots with a -1 charge. How does magnesium atoms and how many chlorine atoms react to formula to make magnesium chloride? Well, if you look up top, 1 Mg, 2 Cl's, magnesium loses 2, 2 Cl's gain 1, and the overall formula is MgCl2. Instead of writing MgClCl, they just write MgCl2. Number 6, what kind of compounds is magnesium chloride? It's ionic. What happens to the electrons during the formation? They go from the metal to the nonmetal. They go from magnesium to chlorine. And what holds them together? They're electrostatic forces, which hold all ionic compounds together. Number 7, what's the formula for the ionic compound with Mg and S? Well, I see magnesium has 2, sulfur has 6. So magnesium we know is going to lose 2, but sulfur only needs to gain 2. So it's going to be MgS, because there's 2 lost, 2 gained, and guess what? That gives me an overall charge of 0.